Hello friends, you are watching ERUDIRE Plus, the professional CAD/CAM solution provider. Let's get started.
Hello viewers, today I want to show CFD heat transfer analysis through a heat pipe using ANSYS Fluent fault tolerant machine. This is the heat pipe. Actually, heat pipe is having high thermal conductivity. This is made up of copper. Actually, heat pipe is considered into three different zones. The first part, the bottom part is known as evaporator zone. The middle one is known as adiabatic section, and finally the top one is known as condenser part. So it is having three different parts: evaporator, adiabatic section, and also condenser part. Based on specific applications, we can make different parts with different lengths, right? And at the bottom we have provided some heat source. To understand the geometry, let us cut it from a specific plane. Let us see the geometry. Through this heat pipe, we have provided some kind of gap. Actually, in a heat pipe, very small amount of fluid is there, and that fluid, when it is evaporated, it rises up by using capillary action. So there will be continuous fluid flow from bottom to top, and again it will come down. Let's see the cross section. Let us see this sectional view from a different plane. Let's see inside this one. Inside this one, we are having very small gaps, right? There will be very less difference in temperature between the evaporator and condenser zone, right? For starting CFD analysis of this one, we need to save this object with FMD extension or FM database. We have already saved this one, so let us close it, and we need to start Fluent Launcher. Let us start it. Initially, we need to start fault tolerant machine, and next to that, we need to import that CAD model. We can import it from here. With customs mode on, let us load it. Next to that, we need to import that CAD model into meshing mode, or we can move selected parts to a new object, and from advanced settings, we need to create separate zone for each part. Then copy settings to child objects, and finally we need to create meshing objects. It is an internal analysis, and in this case we don't require any kind of caps as it is a closed boundary. So with the other default parameters, let us describe the geometry. Next to that, we need to identify fluid regions, and that can be done using different options like centroid of objects, numerical inputs, or offset methods. We'll use offset methods. Let us select zone, and for identifying fluid domain, we need to select any specific location inside this heat pipe. Let us select any one like adiabatic zone. You can see within that adiabatic zone, one diamond shape object is created, which is indicating the fluid domain. Let us identify this region. We don't require any kind of other methods. We can use this one by offset method also. We can move this diamond a little bit up or down, indicating the domain of fluid, as throughout this whole heat pipe fluid will be moving. So we can push anywhere else, or we can move it at the center also, no issues at all. Let us make this region as fluid region. So identify this one, and we can rename this one as fluid region, and let us identify this region. Next to that, we need to create some kind of void region which is required to restrict the flow of fluid from inside to outside. So instead of fluid, it will be void domain, and it will be renamed as void region. Let us select that object. You can see the diamond shape is indicating the inside domain of this heat pipe. So the diamond shape has to move outside to indicate void domain. Let us move that diamond shape outside by using offset method. The diamond shape has to move outside. Let us provide y equals to 900. You can see that diamond has moved outside. Right, this is the diamond shape. You can drag it and see the diamond has moved outside, which is indicating void domain. With this one, let us identify this region and renaming this one as void region. Next to that, we need to define leakage threshold. In our model, we are not having any kind of leakage, so let us update with no leakage condition. You can see here 3 different domains have been created. 2 domains we have created and another domain is created by default, that is object. Object should be actually having solid domain, so let us convert this void into solid domain, and we can mesh different regions with different types of meshing options. Let us consider fluid region and object region to be meshed with polyhexcore meshing. The void region does not require any kind of meshing, right? So with these settings, let us update regions, and with the default mesh control options, let us update. We need to generate surface mesh with the target skewness of 0.8, and from advanced settings, we need to separate contact pairs, that is yes, and global minimum we're considering as 1. Let us generate surface mesh. Surface mesh is created, and what else summary is saying that skewed cells greater than 0.8 is 0, and average skewness is 0.286, maximum skewness is 0.78, and phase count is 15,472. By the same times, left hand side we can see different boundaries have been created and all are walls. In this case, we are not having any kind of inlets and outlets. Let us update these boundaries, and we need to add boundary layers. Let us add 2 numbers of boundary layers. Next to that, we need to generate volume mesh. Let us generate volume mesh. Volume mesh is generated, and you can see from overall summary that quality less than 0.1 is 0, quality less than 0.04 is 0, and minimum quality is 0.2, and cell count is 26,411. You can see mesh quality from here also. Let us check mesh quality. It is showing that minimum orthogonal quality is 2 into 10 to the minus 1, and maximum aspect ratio is 3.7 into 10 to the 1. This is good enough. Next to that, we need to switch on to solution mode. In solution mode, first of all, we need to select units. And we consider length as millimeter, and temperature will be degrees centigrade. Let us close it. We're considering this one as a transient analysis, and gravity will be involved. Direction of gravity will be y. Along y it will be minus 9.81 meter per second square. Before starting models, we can go back to materials, as it is a fluid mixing case. In this analysis, there will be mixing of 2 different fluids. Water will be vaporized, and then it will be mixed with air particles. This will be a multi-phase analysis. So before starting these multi-phase options, we need to provide materials. We are having 2 different types of fluids, air and water. Water can be taken from Fluent database. Let us select water liquid, copy, and the heat pipe is made up of copper. Let us select solid from here, and it will be made up of copper. Copy, close. We have selected copper as solid and water as fluid. Next to that, we can move on to models. As it is a heat transfer analysis, so energy equation should be on. Multiphase should be on. It is a homogeneous model of VOF or volume of fluid. Here we are having two different fluids, air and water vapor, that will be vaporized from water. We are considering implicit body force, that is surface tension and gravitational forces, to be taken care of. Let us apply. Let us see the phases. Phase 1 is primary phase. Let us consider phase 1 is air, and we can rename this one as air. Let us apply. And secondary phase will be made up of water. Phase 2, we can rename this one as water. In phase interaction, we can see it is a phase between air and water, and let us have a constant surface tension in between water and air. Let us provide the value of this one to be 0.1. Let us apply. Surface tension force modeling, we need to check in, and wall addition is needed to have smooth boundary layers. Let us apply. Close. From models, we need to select K omega 2 SST. For this fluid mixing case, we need to consider K omega 2 SST model. Next to that, we need to apply boundary conditions. Boundary conditions should be provided from walls only. Let us consider heat source. It is made up of copper, and it will provide a constant temperature of 100 degrees centigrade. Let us consider wall thickness as 0.01 millimeter. Let us apply and close. Next to that, we need to see different walls. All the walls are made up of copper, and through these walls, it will be transferred through convection. Let us provide convective transfer coefficient as 50 watt per meter square degree Kelvin at a temperature of 70 degrees centigrade. And we are considering wall thickness as 0.01 millimeter. Let us apply and close. Now the same boundary condition to be applied for the remaining walls. Let us copy it, and the same boundary condition to be transferred to the remaining walls. Let us copy. Okay. Let us close it. So all the walls are having same boundary conditions. Next to that, we need to select solution methods. It will be Paisu method and special discretization we are considering Green-Gauss node-based method. Momentum should be third order MUS cell. Next to that, we need to initialize. we'll start standard initialization, and it will be started from all zones. And here in this case, we need to select water volume fraction inside this one. As I told before, inside this heat pipe, very small amount of water will be there. So volume fraction of water, we can say this one is equal to 0.05. That means 5% of water will be there inside this heat pipe. We are considering volume fraction of water as 0.05, and pressure of that one should be very less. We are providing a low pressure of 20,000 Pascal and volume fraction of water as 0.05, that is 5% of water is there. Let us initialize. Initialization is done. Next to that, we need to run calculations. As it is a transient analysis, so let us consider numbers of time steps as 100 and time step size as 0.1. Maximum iterations per time steps equal to 2. Let us calculate. Iterations have already started. Let the iterations move on. Whenever it is finished, we'll see the results and go for detailed analysis. Calculation is complete. Now we can see our results from here, and it will be from reports, surface interiors, facet average, and we're going to see temperature distribution. Through different fluid domains of condenser, evaporator, and also adiabatic zone. Let us compute. It is showing all the 3 different zones like adiabatic zone, condenser zone, and evaporator zone. All are having similar temperature of 96 degrees centigrade. And that is the heat pipe is considering as a good conductor, and net temperature is 96.67 degrees centigrade. Right. Next to that, we're going to see different contours of pressure and temperature through different planes. New contours, and we're going to see contours of temperature through condenser zone fluid, evaporator zone fluid, and also adiabatic zone. Let us display. It will be better to see this one through a specific plane, because at the adiabatic zone we have provided some kind of layers, so we are not getting the temperature at the inside zone. We have a specific temperature at different zones. We can have a view from specific planes. For that, we need to create some planes. Let us create a plane. We want to create a plane along XY. Let us create, and with respect to XY plane, we want to see temperature and pressure distribution. Now, new contours of temperature, and that to be viewed through plane number 7. Let us make the range little specified from 90 to 96. It will be better to have this small range. Let us display. This one is showing contours of temperature through plane number 7. You can see temperature distribution through different locations. Let us drag it and see at different locations. Throughout it is having constant temperature of 96 degrees centigrade. That means this heat pipe is acting as a good conductor. Let us see pressure distribution also. Contours of pressure. Display. You can see pressure inside this heat pipe. At the bottom level pressure is high and at the top level pressure is less. Right. Now what is the mesh distribution through this heat pipe, and we don't want to see edges and nodes. We want to see only faces. Let us display. This is mesh distribution. Next to that, we want to create a scene in between mesh and different contours of temperature and pressure. Let us close it. And we want to see some scene. Let us have a scene between mesh 1 and contour 1. By making the mesh as transparent, let us display. This is showing the temperature distribution. This is a scene between mesh and pressure. Initially at the bottom side, pressure is very high, but as it is moving up, pressure is less, right? We have maintained a very less pressure inside this heat pipe. Okay, with this one we'll conclude our today's analysis. It is a very simple analysis of heat pipe. At the bottom of this heat pipe, we had a heat source where we have provided a constant temperature of 100 degrees centigrade, and we could see the temperature through the different locations of condenser, evaporator and adiabatic zone. Temperature was approximately 97 degrees centigrade. That means it was a very good conductor. Okay, thank you so much for watching this video. Thank you again. Bye. If you like this video, please subscribe and share, and if you have any kind of doubts, please write to me. Thank you so much for watching this video. Thank you again. Bye.